Welcome to this video from LearnElectrics, where we try to answer the question of how fast electricity travels and why does it seem to be instantaneous, or maybe not. And we promise to keep it simple and understandable. This came about after several people asked about electrons and what they were, how fast they travelled through a copper wire, and so on. Inevitably, someone asked if that was the same as the speed of electricity, and did things happen at the speed of light? We can look at this, discuss current flow, and delve into what makes an atom from the electrical point of view. Just be aware that the understanding of electricity is a developing science. Lots of theories abound, and many previous good ideas have been overtaken by modern thinking in the last 50 years or so, and may change in the future. To begin with, before we look at how fast electricity travels, and there are two speeds, we should understand the atom from an electrical science perspective. All matter is made up of atoms, elements, as any good book on the periodic table will show you. Hydrogen is the first element. It has one proton at the centre and an orbiting electron, as shown here in this Bohr model representation. It has an atomic number of 1, as there is just one proton. Helium has an atomic number of 2. We know then that there are 2 protons at the centre and 2 electrons in orbit around them. Helium has 2 protons and thus an atomic number of 2. Helium also has 2 neutrons, and the neutrons and protons at the centre make up the atom's nucleus. Lithium, as used in batteries, has 3 electrons and a nucleus of 3 protons and 4 neutrons. Notice that the number of protons, the positively charged particles, is always matched with the same number of electrons, the negatively charged particles. 3 protons, atomic number 3. The number of neutrons does not have to match the atomic number, and this is where we get isotopes from. Copper has an atomic number of 29, and therefore 29 electrons in orbit and 29 protons at the centre, along with 35 neutrons. Again, the neutrons do not need to match the atomic number. Neutrons play no important part in the electrical theory of this video and will not be discussed further. Now we can look at this thing called a valence electron. This is how we get electricity, the thing that makes the difference between a good conductor and a good insulator. Each of the electron rings around the nucleus is called a shell, and there is a preset maximum number of electrons per shell. Here, the first shell has 2 electrons, then 8 electrons in shell number 2, and 18 electrons in the third shell. The fourth shell could also have up to 18 electrons, but it has only 1. This means that this single electron can easily detach from the atom, or indeed, an electron from another atom can join it. Gold and silver are good conductors of electricity, just like copper, and they also have a single valence electron in their outermost shells. We should try to visualize a central nucleus surrounded by all their electrons which swarm around the nucleus in a cloud. Sometimes an electron will pass close to another atom and jump to that atom, backwards and forwards, in a random manner. But if we can apply an electrical force to the circuit, we can make those loose electrons, the valence electrons, all move in the same direction. They will no longer move randomly, but will instead move as a flow of electrical current. Make enough of them move together and we can do things with them, make lights come on, boil water, etc. How do electrons move? A good question, and for that we need to look at electrons and this thing called holes. Imagine these copper atoms in a piece of wire, each with its own valence electron, this loosely attached electron in the cloud around the atom. What happens if an electric force is applied and the electron indicated leaves the atom? As it jumps to another atom, imagine it leaving a hole behind, as shown. The atom now has only 28 electrons, but it should have 29, so it needs to attract an electron. And the other atom now has 30 electrons, and it needs to push one off somewhere else. A valence electron from another nearby atom will join the orbit around the atom. This will complete the 29 electrons that the atom needs, but has left a hole in the donor atom, and so the story repeats. And this is happening with all the atoms in the copper wire. They are moving to the right in this example, and the holes appear to be moving to the left. Because an electrical source is acting on them, the electrons have direction. There is current flow. Now is the time to look at conventional current flow and electron flow, two different ways of looking at the same thing. Imagine a wooden board with a series of holes drilled into it. In each hole is a marble, except for the hole on the furthest right. The rightmost marble can move into the hole to its right. This leaves a hole into which the next marble can move. This, again, leaves a hole and an opportunity for the next marble to move to the right. And so the process repeats itself. Marbles move to the right and holes move to the left. The question now is, has the hole moved or has the electron moved? And this will show the difference between conventional current flow, where we now imagine holes moving, and the more modern electron flow model. If we take a simple resistive circuit with a DC source such as a battery, which way does the current flow around the circuit? Positive to negative or negative to positive? In conventional current flow, as it was imagined at the start of electrical engineering and electronics back in the 1800s, it was assumed that current flowed from the positive terminal of the battery to the negative terminal. This was simply because nobody knew any different. It was the beginning of electrical science, and nobody had the research facilities and technically expert universities that we have today. Most of us still look at circuit drawings and imagine the current flowing from positive to negative, what is called conventional current flow, or hole theory, following the direction of the holes, and I know that I do that. Now we know that electrons move from negative to positive. It is electron flow that makes up electrical current, and this current is flowing from the negative terminal of the battery to the positive terminal. Whilst we are on the subject of batteries, here is a useful memory jogger to help you to remember which is the positive terminal of a battery and which is the negative. And we've all forgotten from time to time. This is the symbol for a battery, one long line and one short line. Which is positive and which is negative, and this is how I remember it. The long line can be chopped in half, and the two halves can be rearranged to make a plus sign, a positive. So the long line is positive and the shorter line is negative. Remember it, it will serve you well. Okay, on to hole theory and why it doesn't work. As we said, for the first few decades of this new electrical science, it was always assumed that current flowed from positive to negative. And then new devices were invented that transformed the world: valves, transistors, integrated circuits. Up until recently, televisions operated with valves, and the actual TV screen was a cathode ray tube. If we look at this partial drawing of a battery-operated radio set using valves, sometimes called tubes, we can see the dilemma. Conventional flow, positive to negative, was proved wrong when electronic valves or tubes were invented. Holes could not travel across a very obvious gap in the valve. It was not possible for nothing to jump across nothing. It had to be something else, something physical that jumped across the gap from one side to the other. Electron theory will work with our electronic valves. Electrons are physical objects, and it is now proven that electrons move. Electrons can physically jump across the gap in the valve when given sufficient stimulation from the circuit. Current flow is therefore from negative to positive. But there is nothing to stop you imagining current flow from positive to negative if it works for you. It works for me, and many designers still imagine a positive to negative flow. And hopefully we now understand a little more about atoms and electrons. So let's look at the speed of electricity, a popular question with two answers. Today, we believe that electrons in a copper wire will move at up to 1 centimetre per second, which is not very fast. So the next question is, why do the room lights come on instantly when the switch is operated? It is now believed that electrical current flows as a wave with all electrons moving together at more or less the same time. And we can say that the copper wire is preloaded with electrons, even with the switch turned off. They just need the instruction to start flowing. The theory says that, as there are already valence electrons in the copper wire at the light bulb, when the switch is operated, the electrons at the switch move, and so do the electrons at the light bulb. Almost instantly, they all move together. And the wave will move at close to the speed of light, not at 1 centimetre a second. So what we are saying is that an individual electron might only move along the wire at 1 centimetre per second, but the effect of the electrical wave is felt instantly at almost the speed of light. And this, the speed of light, is 300,000 kilometres per second, or 186,000 miles per second. Let's do an example of this to help explain it. Let's make up a hypothetical scenario to explain speed. And as most people in the UK can relate to inches, yards and miles much more easily than kilometres, then miles per hour is what we will use here. And besides, the numbers work out a lot better. Imagine that we have a wooden pole 1 mile long, with a nail in one end of the pole. The nail is representing an atom. If we move the pole to the left by just 1 inch every second, then the nail is moving at just 100 yards per hour. There are 3,600 seconds in 1 hour. Divide this by 36 inches to the yard, and we have 100 yards. Now imagine the nail is an electron in a piece of wire, moving at 100 yards per hour. But the effect of the nail moving is instantly felt 1 mile away. As soon as the pole begins to move at one end, the pole also moves at the other end. And this effect of the nail moving is felt at 3,600 miles per hour. 1 mile every second, 3,600 seconds in 1 hour. There's a difference between nail movement and pole movement. There's a difference between electron movement and wave movement. The electrons will move at 1 centimetre a second. The electrical wave movement will be felt at close to the speed of light at 300,000 kilometres per second. To give you an idea of the speed of light, a photon of light could, in theory, travel around the world at the equator just over 7 times every second. 7 times a second. Or imagine a water tap. This is another way to think of the difference between electron speed and wave speed. When you turn a water tap on, water comes out of the tap almost instantly. But this is not the water that has just entered the water pipe way back in the street. It is the water that was already in the tap, waiting to move forwards. The water entering the pipe pushes the water out of the tap, and its effect is noticed immediately. And so, a very short recap on this very simple introduction. Valence electrons in conductive materials, copper, silver, gold and other metals are only loosely attached to each of the atoms and can be easily dislodged. They are free to move between other atoms. An electrical force will cause these electrons to all flow in the same direction, an electrical current. An individual electron may only move at 1 centimetre per second, but the effect of the electrical wave is felt almost instantly at over 90% of the speed of light. Conventional current flow, the way that most of us think, supposes that current moves from positive to negative, and most electrical circuits are still analysed in this manner. It works in theory. In a physical sense, it is now established that current flow is electron flow from negative to positive. It is electrons that move about. Thank you for watching. It really is appreciated, and I hope that you found this video useful and informative, with a little more knowledge sneaking into your mental toolbox. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at LearnElectrics.com. And don't forget, you can also type in LearnElectrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.